So my name is Guillaume. I'm a PhD student at EPFL working on Dotty, the new Scala compiler. And today I'd like to talk to you about how we are dealing with IDEs and how we're trying to get a good developer experience for people in preparation for Scala 3. So I guess I can skip that slide because everyone has seen the keynote, right? But just to recap, so Dotty is this new research compiler that will eventually become Scala 3. It has a completely redesigned internals, but from the user experience point of view, it's pretty similar. And of course, check out the website and the blog post on Scala Lang on the Scala 3 roadmap. But Dotty, to me, is also a chance to redesign some components of the language. For example, we managed to improve how incremental compilation works by just redesigning the thing from scratch and finding issues. And some of these fixes got back into Scala 2 afterwards. We also managed to improve the pattern matching exhaustivity checks. And the algorithm has even now been reused in Swift for their pattern matching. And of course, there's a bunch of other areas like that. And today I'm going to talk about tooling, because a good developer experience, of course, requires good tools. So we have a REPL. It even has syntax highlighting like Ammonite. In fact, we stole some code from Ammonite to do that. We have a documentation generation tool that we use to generate all of our documentation. And of course, we have IDE support. So first, a brief recap of, let's say, the state of the art of IDE support in Scala land. So there's two kinds of IDEs, really, in Scala. There's the one which are based on the Scala presentation compiler, which is just a special mode of Scala C. These are the Scala IDE, the Eclipse plugin, and Enzyme. And there are re-implementations of the Scala type checker, or more exactly, there's exactly one re-implementation, because who will be crazy enough to do that, right? Which is the Scala plugin for IntelliJ IDEA. So all these things solve kind of the same problem, but they're all kind of difficult to reuse for our purpose, for a new compiler, because they kind of depend on details of the previous language. And they're all kind of big, except Enzyme, really, which is quite nice and small, and also has this nice server-client design that I'm going to talk about later. So anyway, so let's imagine we can't reuse any of that stuff, so we want to start from scratch. So what do we do? First, we start with a set of design principles. And the design principles I want to emphasize are code reuse, as much as possible the compiler and the IDE should share code so that you don't have bugs which are IDE only and impossible to reproduce and very hard to debug. We want editor agnosticity because some editors are popular some days and not popular the next day. So you can't force everyone to use some editor. And we want it to be easy to use and to install. Like, it should be as simple as possible. So let's go in details through all these principles and see how we can implement them. So to talk about code reuse, I'm going to talk a bit about how the compiler works. So the compiler is this giant pipeline of phases, basically. It starts with your source program. It parses that into an untyped abstract syntax tree. Then it type checked that abstract syntax tree. That's when you get most of your error messages. And then pretty much everything after that is just a bunch of simplification and transformation phases for trees that make them easier at the end to be emitted as JVM bytecode or JS or LLVM. So typer is the one we're interested in to do querying of a compiler, and I'll explain why. So imagine you have some source code. You have a final val called lm, whose value is 1, and some other val called foo, which references LM. And this little flag here is your cursor position in your IDE. And at that point, the user makes a query. He wants to do a jump to definition. So he wants to go to the definition of LM. So if we look at the tree after type checking, and if we print it to make it nicer to read, it's pretty similar to what we had before. We just have types inserted everywhere. We also, and this isn't shown in the pretty printing, have a position for all the nodes. That means that we can answer the query, because we can just look at the type of LM, and it has a very precise types from which we can find its symbol, and from that we can traverse the tree to find its definition, and at its definition we have its position, and then we can send that back to the IDE, so the IDE can execute go to definition. But if we go a little bit later in the compilation phases, now we're in trouble. After constant folding, LM+1 has been replaced by 2. So some information has been lost. And that means that at that point, we cannot answer the query anymore, because the information that we need, what's the element at the position where the user cursor is not present anymore. So to recap, to query the compiler, we need to start trees right after type checking, and not at any later point, because at any later point, we already start losing information. And we can respond to IDE queries by traversing these trees. That leaves one big question and answer is, what do you do about code that has already been compiled? So all of this works if you're in an IDE, in a file that is open, and as you type, the IDE is going to type check that file. But usually in a project, you have many files, and most of them are not open in your IDE. They're sitting in your disk, already compiled, so you have class files for them. So to understand that, we need to go a little bit later in the compiler pipeline and talk about pickling. So pickling is used to add some extra information that will be present in the bytecode that can be used for various purposes. In Scala 2, we store the method signatures in the pickling information. This is necessary because the bytecode we emit is JVM bytecode, which does have information about method signatures, but it's already erased information because the JVM doesn't know about type parameters. Certainly it doesn't know about hierarchy type parameters or any complicated type features. So all of those disappear from the bytecode, but we still need to store them somewhere so that we can reuse them when we do separate compilation, when we read some class file of a library you're using. Dotty does the same thing, but it goes further. Instead of just storing the method signatures, it stores full trees. And that's what we call tasty, which you've also heard about in the keynote. So to recap, the original motivation of tasty was to solve the binary compat problem. If you always recompile using binary JVM bytecode as your dependencies, then when the compiler changes its encoding, say when in 2.12 the trait encoding was changed, you couldn't reuse 2.11 classes in your 2.12 projects because they're just completely different encodings. So instead, you could always recompile from source code. But if you do that, if the type checker changes, if, say, implicit search changes or some details of type inference changes, then your code might stop compiling. So tasty is kind of an intermediate between these two things where we store the abstract syntax tree just after type checking. So we've already done implicit search, overloading resolution, type inference, but all the details of the implementation, like how our traits encoded, are not present in this abstract syntax tree. So you can recompile everything from that, assuming that tasty stays binary compatible, which is the trees we store in tasty are exactly the type trees we were using previously to answer queries. So what we can do for everything that is compiled in your class path is just deserialize the tasty and query these trees. And that's very interesting because it means that we have one uniform way of dealing with everything from things open in your IDE to things in your class files to things in your dependencies. It's just all trees, and we can reuse the same code to query them, which means less code, which means less bugs. So to do this, we have a very small set of interactive APIs, which are part of the compilers, that deal with tree traversals, with the lifecycle management of a compiler. And we already use them, some of them, both in the IDE and the REPL. For example, for completions, you want the same mechanism to be used and not a reinvention of the mechanism when you're doing completion in the IDE and in the REPL. And there's more things we could do in this APIs, like interruption handling. Say, every time you press a keystroke in your IDE, currently it's going to recompile the full buffer. And it won't stop until it's done compiling the full buffer, or just type checking it, not fully compiling it. Which means that you might have some delay when you're typing very fast. So we should be able to interrupt previous type checking to avoid that. We haven't done that yet, because surprisingly, this delay is not a big deal most of the time, because at least when using VS Code, all the UI is completely asynchronous. So even if the backend is like busy type checking, that doesn't affect your editing experience much. It's mostly transparent. And all of that is less than 1,000 lines of code so far. So the next big goal we have is to make this work with any IDE. Right now we're focusing on VS Code because of reasons I'll explain later, but we really want everyone, whatever IDE they're using, to be able to use this. Or even if you're using Vim or Emacs or Ed, if that's your thing. So there's the problem we're trying to solve here is the IDE portability problem. If you have M IDEs and you want to support N programming languages, you need M times N IDE plugins. That's a lot. And that's also problematic because to write these plugins, you need to be both a language expert and an IDE expert for every combination of language and IDE. And usually, IDE experts are different people from the language experts. So we'd like to have like some division of work. So the language server protocol is a formalization of that kind of things. It's a protocol that Microsoft first created for Visual Studio Code, but has now been implemented by a bunch of other editors and other languages. The way it works is it's based on JSON RPC, which is just a thin layer of how do you send messages back and forth in JSON. So the IDE is going to notify the language server about user actions. Say the user press the go to definition button. On its side, the language server is going to maintain some internal representation of the code, probably a type check representation, so that it can answer queries. And it can also notify the IDEs about things like warnings and errors that it finds out. And then the IDE can send requests triggered by user actions, say the user wants to rename something. And it's completely asynchronous and cancelable. So you should never have to like wait for your compiler to stop compiling to be able to type your code, because that's like different things, really. So how do we implement a language server for Dotty? So first, all the low-level message handling, we just use Eclipse LSP4j, which is a library, a Java library, because we can't really use Scala libraries in a Scala compiler, or we run into loops. But LSP4j is very nice because it does all the low-level stuff for us, and basically we only have to override methods to implement messages. We rely on the interactive APIs I presented in the previous section. And that means that in the end, it's only like a few hundred lines of code to implement a language server. Just to show that there's basically no magic, I can show you the implementation of go-to-definition. So we override a method in an interface that LSP4j provides for us. We take parameters, which are the For go-to definition, the parameters are going to be the URI, which represent which file you're in, and the position in the file. And that's it. That's all the information you get from the protocol. And using that information, you have to figure out how to get a position of a definition that you can get to the user. So to do that, we need, of course, from the URI to find out which project it belongs to. Because usually, in a typical SBT project, you're going to have many sub-projects, each with their own compiler flags, maybe even their own compiler version. So you need to figure out which projects your URI belongs to. Then we get a context, which represents the internals of the compilers. Then we just do some boilerplate to translate from positions as represented by LSP4j to positions as represented by Dotty. Then we look at all the type trees we have for the current URI. And then we can use our interactive API to find out where are the symbols that match this position, the symbols referenced at this position in the trees. And from that, we can find where that symbol is defined, in what class it's defined. And from that class, we can find the tree of that class. And again, that tree might either be open in your IDE, or it might come from some class file. And from that, we can then traverse that tree and find the position of the definition. And then we just return that position. So last but not least, we also want our IDE to be like an amazing user experience. Like people should be so happy that they can use this without twiddling with configuration files and stuff like that. And for now, what this means is we need to do SBT integration. So the way this works is we analyze the build to find Dotty projects using an SBT plugin. We compile these projects. We generate configuration files. We install the Dotty VS Code extension, and then we launch VS Code. And we do all of that if you type the launch IDE command in a Dotty project. And that works in any Dotty project because the plugin for IDE support is just part of the plugin you need to use for any Dotty project. So it's already built in. So briefly, the configurations files we generate, there's one which tells the artifact to use to launch the Dotty language server. So that's just going to be like, we need to launch this version. Then we're going to fetch this using Coursier. Coursier is awesome. And we have another configuration file, which basically is a JSON representation of your SBT build. So all your subprojects, and for every subproject, the source directories, the class path, the compiler version. So all of that is very annoying to maintain, of course, because if you want to support multiple build tools, you need to make a bunch of plugins, and you need to make sure that they all do the same thing. And then you still have the issue with like synchronization, because between the time that you generated that file and the time that the user opened the IDE, maybe something changed. So what if instead of querying the compiler using plugins to generate files and then reading these files later on, we could just have some kind of protocol to interactively ask the build tool, hey, can you give me all your projects, which are Dotty projects, which correspond to these source directories? And that's what the build server protocol is about. And Jorge and Martin have a talk on exactly that you should definitely see. So it's like the 1.0 version was released recently, I think. For now, it's only implemented in Broop and IntelliJ. But my hope is that everyone will use this thing eventually, and then I don't have to maintain SBT plugins, because that's not what I consider fun. But to get to the seamless, fantastic user experience, we also need a discovery protocol, which is like our answer to the question, how do I start a build server for this project? Because each build tool might have its own way to start a build server and then to communicate with it. So I really think we need some very simple way to say, this is the command line you need to run, and we put this command line in a file, which is in a central location that is the same for all kind of projects, for all build tools. So that part doesn't exist yet. All right, so just to recap our design principles, for code reuse, we implemented some APIs for interactive usage that we use in different scenarios. And these APIs are just reusing internal compiler stuff that we know should be correct because we test it heavily. For editor agnosticity, we implemented the LSP. And for ease of use, we have one command, but we can do better. We should be able to do 0 commands. So I can do a quick demo, maybe. I can try. So if you want to follow along, you can go to lamppfl, GitHub lamppfl Dotty example project. And you can clone that thing. And you can go to the code of the Visual Studio Code thing and download it. And if you do both of these things, and then you just type so this is an example project which demos a bunch of features of the language. And if it's working, yes, I can say go to definition. It goes to the definition. I can, this is Scala util write. I can do find all references. Finds all references. Okay. If I'm very daring, I can even do rename. So that one is less well tested so far. Let's see, is that thing used? Yes, so I can try to rename it and see what happens. Yeah. And it usually works with multiple files. So like if you have references in other files, it's going to open these files in your IDE and do the renaming. So we have go to definition working, we have find all references, we have completion. Say if I do m dot, lots of symbolic. So all of that mostly works. We don't yet have documentation support, so if I over this thing, I don't see the documentation, but this is coming very soon. We have an open PR by Martres and Guillaume that implements that, and that's going to be awesome. All right, I'm going to keep going a bit. One window. So this is cool, but nowadays that's just like standard stuff. Now people want more. People want debugger support. And this one is interesting because when I first tried to look into this, it sounded very hard. But it turns out that I think we can get it working without too much work. So it turns out that Microsoft helpfully made a Java debug server based on another protocol, which is called the debug adapter protocol, which so far I think is only implemented by VS Code, maybe Atom too. But I hope is also implemented by other IDEs. And so the fact that this Java debug server exists is very interesting for us because the way this works is just it's an interface between the Java debugging interface APIs and the debug protocol. And the same debug APIs that Java uses, of course, can work with Scala if you compile your Scala code to Java. So most things just work, but not enough that I can merge it in Dotty yet. But one big challenge is expression evaluation. So I'm going to explain what this is. So imagine you have some code. You have a class with two methods, And now this is your breakpoint. This isn't the cursor anymore. I'm reusing emojis. And at this breakpoint, your program is stopped, and you want to evaluate the expression foo. So how do you do that? Because remember, there's a running JVM somewhere with your program, and then you have your debug server that is communicating with that JVM. But you can't really send Scala comments to that JVM because the JVM doesn't speak Scala natively. The best you can do is use the Java debugging APIs to send it very low-level comments. And here we want to run foo, which means we need to do type checking because we need to do implicit search. So how do we do that? So first, we're going to run the normal compiler pipeline. So we're going to introduce foo and put it like, we're not going to actually edit the file, but we're going to pretend we've edited the file and send that to the compiler with foo introduced at the breakpoint position. Then we're going to run the compiler pipeline I showed you before. But we're going to stop just before we get to emitting JVM bytecode. So at this point, all the implicits have been erased and resolved, and some other changes have happened to the code. So we know now that the expression we want to send to the JVM is this.foo of y. We still don't know how to send that to the JVM, because this is like some code somewhere deep in a method, and the JVM doesn't know about the methods we just compiled. So we need to extract this to a static method. So we can do this using a special compiler phase just for the debugger. So we're going to lift our expression to a static method that takes as parameters all the things it references. So here there's just a this and a y. And then, because the JVM doesn't know about our list of parameters either, we need to go a bit more abstract still and make an exec method that takes a self and the list of local variables in your stack frames. And from that, if we can send that to the JVM, then we're good. But again, this is still code in our local VM, which is talking to a remote VM. So how do we do this? So we're going to do this in a very quirky way, but the simplest way I could think of is we're going to compile this static global object to a class file. We're going to somehow send it over to the remote JVM, and then we're going to ask the remote JVM, hey, can you call global.exec with the right arguments? So as a shortcut, I'm going to pretend this thing is in the standard library because I put it in the Dotty library. So this thing is just about doing remote code execution on any random program you have by sending it a class path and a self and a list of local variables, and then using class loading tricks to run that code at runtime. So basically what we want to do is figure out the class path of the object we just compiled, find the reference to the this in the stack frame, make a map of all the local variables in our stack frame, and then do a remote call of debug eval with all this stuff. And it's really terrible, ugly code, but it's doable using the JDI APIs. So I won't go through the details, but basically you can resolve the thing into executing that stuff. And by the way, to contrast this with how, say, the Scala IDE does debugging, the Scala IDE does debugging by basically taking your expression and then doing about 20 compiler phases of transformations to try to transform that into expressions that can, into basically calls to the JDI APIs. So every Scala feature, basically, they re-implement using the JDI APIs. So as you can imagine, that's like very complicated, and their implementation is 8,000 lines of code. Whereas this hack is like a few hundred lines, I think. And just to show you that this actually works, I'm going to try to do a second demo, because I'm very daring today. So this is VS Code again, but this time we're using it on Dotty itself. So the way debugging works is you have a launch.json file, which is automatically generated at the first time you do the debugger, you run the debugger, where you can specify, say, what the main class is, what the project name is, the arguments, etc., the class path. So we're going to run using our debugger, which is our compiler itself, to compile something. So we're going to compile. Oh, this is too big. So just a dummy object with a field of type any that contains an int. And this example is non-trivial because this is a primitive, and this becomes object on the JVM. So there's something that happens somewhere in the compiler. And this something is called boxing, and it happens in Erasure. So if you go to Erasure, you'll find a method called box. So we can put a breakpoint on that method. And then we can press F5 and hope nothing crashes. Yes. So on the left, you already have, so all this stuff is basically what we get for free thanks to Microsoft Java Debug Server. This is the stack frame, and you can dig deep into the stack frame if you want. So we have a tree, which has a field called const, which has a field called tag. We have a call stack of all the methods we called, and we can jump back and forth. And on this side, we have our code. And we already have these cool things where I can hover over some variable, and if it's something which is on the stack frame, I see its content right now. But then the interesting part, the thing I actually did and did not steal from Microsoft. Let's see, I can type println foo and print foo, and return something of type box unit. I can type tree, and I get back my tree. Oops. I don't get back my tree because tree is not in scope in that line. But anyway, so we can go deep into that method and just look at what is going to return in the end. So in the end, we get to that line, and we can check that, in fact, arg is empty. We get a Boolean. And Boolean is false. Yeah, so there's boxing going on, but I can also do print. All right, now, so what's going on here? So class, what's that? That's just some symbol. If I print it, I see that symbol is class int, which makes sense, right? And then on this symbol, we call box method, and then we call ref on that. So you can probably already guess what that kind of does, but we can run it and see. So we got ident of box. So ident is a kind of tree, but this isn't a very nice representation of a tree because it's just the raw abstract syntax tree. And usually what we want to do is pretty print it for debugging. So we have a .show method for pretty printing. But that .show method takes an implicit context. And that'd be very annoying to pass that by hand. But hey, we're actually running the full compiler here, so I can just type .show, and it's going to do implicit resolution by itself at runtime, yes. So here we get scala.in.box, which is the pretty printed representation of that tree. And Now we can go further and say, well, what does this thing apply to this thing do? Well, you can probably guess this is going to apply the two things together. So I do apply to tree, and I get scala.in.box of 42. And maybe you don't know what scala.in.box does, so you can also type that here. And you say, well, but I guess an integer whose value is 42. All right. So there's a bunch of more things we want to do and we haven't done yet, like optimizations, more features, because this is what we're all about, adding features everywhere. So one big one is documentation on Hover, which is coming very soon. And of course, we're also interested in a better build tool integration, hopefully with a build server protocol, less soon, but hopefully soon-ish. And there might be even more things we can do. Say, what we have in the debugging panel in VS Code is kind of a REPL, but it's a very limited REPL because you don't have all your nice syntax lighting of your REPL or features like that. So I think it makes a lot of sense if we made our REPL also a client-server model. So we could use the regular Scala REPL to connect to your debugger and to get all the experience you get from a regular REPL. And maybe you could even connect that to like a Jupyter kernel or something. All right, so to conclude, I think it's important to design your compiler with interactivity in mind, because a lot of features we're seeing here only works because we've tried to take interactivity into account when designing various parts of Dotty. For example, Tasty was not at all designed for the IDE features originally, and it sort of worked. But we had to be very careful to preserve all the shape of trees that the user wrote and all their position much more precisely for the IDE features, even though that doesn't really help for any other kind of usage of Tasty so far. You should also design your build tool with interactivity in mind, because if you don't, then everyone has to hack around it in terrible ways. And I think once we do that, then we're free to like expand our minds and make interactivity go beyond what IDEs and REPLs currently offer. And if you haven't read it, you should check out the book Type-Driven Development with IDEs by Edwin Brady, which is sort of a glimpse of the kind of things we could do if we didn't have to solve the basic problems over and over again. So hopefully we'll get there and do even more interesting stuff in the future. Thank you.
Any questions?
Hey, great work. I might have missed this. You mentioned in the beginning when you mentioned cancelable and non-cancelable compilation when the IDE is doing a per keystroke compilation. Is the Tasty tree being recreated upon every keystroke, or is it just being incrementally added upon?
So the Tasty tree is only generated currently when we do a full compilation. For things which are just open in your IDEs, in buffers, we just type check them, and we keep that in memory. We only go to Tasty when we need to read something from disk.
Okay. And also, where can we find the current work in progress for Tasty? Is it on a branch on Dotty?
So most of it is just in master already, okay. Most of Dotty, of Tasty. And then stuff like the documentation support is also something that will become part of Tasty, and that's a pull request by Martin.
By whom?
By Martin Duhem, who's sitting right there.
Okay.
This is a question about tasty. So are we, right now we have all these class files. I mean, we have jars stored in Maven repository, right? I mean, in the archive or any of the repositories we have in the organization. So will we start storing tasty trees also? How is that going to work?
Yeah, so the question is about how is tasty enough, because you might have a lot of class files from existing projects, from even Java projects, and the answer is probably not. So I didn't mention it in the talk, I guess I should have, but there's this project called SemanticDB, which is about generating basically what amounts to an index of the kind of things you could do for IDE, for semantic features in an IDE. So like for every symbol, what are all the positions for its reference, that kind of things. And SemanticDB is language independent. It's there's a Java implementation which reads class files, I think, and there's a Scala compiler plugin also. And so that kind of things can be seen as sort of an index of what you could get from querying tasty directly. So I think that in the end, we want sort of a mix of the two. Use tasty for your local project, and for all your dependencies, you'd use some index, which might be the SemanticDB or some other formats.
So the distributions will continue to be jars, actually.
So for Dotty projects, we basically ship the tasty as part of the class files, as an extra section in the class files. Okay. They might become separate files also in the jars, but they'll always be in the jars because you need them just for separate compilation. They don't add too much to the size of the jar because they are pretty well compressed. So it's a reasonable thing to have in all your jars.
So the second question is about the remote execution of the codes, right? Do you see any potential security issues with respect to them?
Security issues?
For
so
remote debugging.
The question is about security issues with remote debugging stuff. So the class I added to the standard library for my experiment is kind of questionable, but it's actually not necessary. We could do everything I do with this class using just Java debugging interface API remote procedure calls. So just manually calling java.lang.class loader whatever. We can do that using remote calls. So it's not more of a security issue than everything in the JVM already.
Is there any path by which any of this work could benefit Scala 2 users?
Yes. So on the just general IDE front, it's kind of hard to reuse because we depend on tasty, we depend on the internals of Dotty, but I don't think we need to because there are other language server implementation for Scala 2. I'm especially thinking of Metals, which already deliver very similar kind of features and which are very tuned for Scala 2. But for the debugger, the basic principles I use of hacking around the Java debug APIs to shove code into your remote VM, that's something that could be easily reused in any implementation for Scala. So yes.